All right, legends, this is Mr. Maze here, coming to you through the virtual space, and I'm settling in. I hope you're sitting down somewhere comfy, got a cup of coffee or tea, maybe an energy drink if you're that kind of person, or a cup of water is acceptable too. And you're ready for this, which is, if you can believe it, take a breath, the final set of new content notes you will get this year. There are only many other videos that I hopefully make to help you review and to prep. And there will be a pro tips video posted soon for this unit. But this is the very last of our new content stuff. So let's go ahead and walk through. Hopefully you've pulled up your, hopefully you've gone ahead and pulled up your PowerPoint slide for confidence intervals and inference for regression, but that's what we're doing today. Today we're taking regression and we're going to see how it is that we can use confidence intervals and hypothesis testing to further understand a regression line. Now, I'm going to start with hypothesis testing. So let me move over to red here. As you know, anytime we do hypothesis testing, we're going to roll with phantoms. And phantoms is coming back one final time, peeking its wondrous ghostly head into our worlds so that we can use it for the express purpose of seeing what the odds are that a relationship of a sloped line is actually definitively showing a correlation. So the idea of hypothesis testing for regression is, hey, if as x increases, y increases, so we have a positive direction, is that positive direction strong enough that we can actually argue, yes, they are positively correlated? And similarly, if they are negatively correlated, as x gets greater, y gets smaller, can that negative correlation be strong enough that we can actually argue there is a negative correlation? Or is it so weak that it's negligible? Okay, so that's the idea here. What we're asking ourselves is, for hypothesis testing, is the direction either negative or positive strong enough to be significant? Excuse me. If it's not strong enough to be significant, we fail to reject the null. And if it is strong enough to be significant, we can reject the null. So let's take a look. For P, the parameter, you can see in your slideshow, it's going to be as follows. Beta, or B, and it's the uppercase looking B. So this is going to be the true slope. And we're saying that the B, the beta, is the true slope of the line that predicts y, whatever y is in context, from x. And that's the goal. The idea is to say, in your parameter, let's have beta, capital B in this case, equal the true slope of the line that predicts y from x. Our hypotheses are as follows. Our null hypothesis will be quite easy. It will always be that beta, that slope, is equal to 0. And the reason why is that would involve no relationship. If there's no negative or positive direction at all, it's simply a flat line, then there is not enough direction. Obviously, there's zero direction in which to create a correlation. So we're hoping, or we're hoping that there is enough direction that we can fight the idea that the slope is 0. But if that direction is negligible, it's as good as it being 0. On the other hand, our alternate is going to be that same beta is either less than, or greater than, I should say, less than, I just wrote it twice, greater than, less than, or not equal to 0. Right? So we're either arguing, no, the true one is greater than, so this would be for positive, less than, this would be for negative, or simply not equal to, different than, not, it has some kind of linearity, I would say, that's useful. And it's linearity and direction that can effectively show a correlation. All right, so that's what we've got. We've got our parameters set up, we're good to go, and we've got our hypotheses. Either the slope is equal to 0 truthfully, or the slope is not equal to 0 truthfully, either because it's greater, less than, or just not equal to. Our assumptions are a little different this time. Now, some of them are the same. We use LINER as our little acronym for this one. The ones that are the same are independence. For independence, we're doing the same thing. 10 times the sample size should be less than the population. Okay, we know that. The L is a little different here. We need to show that it's linear or be able to argue that the scatter plot is linear. So when you look at the scatter plot, ensure it's not curved. If it's not curved, it's linear. Ensure it's not curved and that it's not non-directional, right? Without direction. The third thing is that it's approximately normal. And when we say approximately normal, in this case, as you can see from the slides, we're talking about the actual separations, right? We don't want it to just be like when we look at that idea of normalcy, it's not just like staring at the actual scatter plot. We're looking at the residuals, right? So the idea is, are the residuals normal when they are distributed? Normally in a histogram, okay? So they'll show you like a histogram of some kind or a plot of residuals, and we'll need to see that those residuals are normally distributed. Or, as you know, the central limit theorem is the other option. Both are possible. So if one goes wrong, the other one can save us. And that is that the sample size is greater than or equal to 30. All right. Then, of course, R is random, and we know what that is. It should be stated in the problem. And the final one, heroes, is going to be this idea of equal variability or constant variability. Now, what does that mean? Well, equal or constant variability is clarified in a slide or two, but let me show you an example of what unequal or non-constant variability would look like. If I did a little graph here, okay? Let's make a scatter plot. What I'm about to show you, this would be considered not constant variability. Now, I'm going to make a line. That's our line of regression. Now, if you look at this graph, what I want you to notice is that even though it's linear, as x gets greater, and actually let me see if I can adjust, the size of the line. As x gets greater, y does get greater as well, but you'll notice that it like phones out, okay? Kind of like a megaphone or a cornucopia. What that's saying is as x gets greater, y also gets greater, but the variability is changing. The variability was tighter at the start, and then it got looser, right? It got weaker because of more variability as the graph goes on. And that is not constant or equal variability there. That is unconstant variability. That's actually, more variability exists later on than earlier on. And that is a no-go. We need to have a graph, on the other hand. What we want to see, I'm going to show that now. What we need to have is a scatter plot that has consistent variability. Now, it doesn't matter if it's high variability or low. The dots can still be kind of a bit all over the place. But see, that would be relatively constant variability in its nature, right? All the plots are about as spread out, all the dots, I should say. If you can call some of these dots, my goodness. Look at those squiggle C's. All these dots are approximately, as spread out from the theoretical residual line as one another. They're all evenly distributed in that way. Okay, so now you know all your assumptions that you're going to need. We're rolling right along. If you take a look in the slideshow, beyond your assumptions, I have a series of different examples of situations where you have each one of the liner elements broken, and then a couple of questions that are multiple choice where you can practice those yourself, so do those in the slideshow. We're now going to move on to the end where we name our test, and it's quite easy. It is the t-test for slope. That's it. We're calling it a t-test for slope. You don't have to say anything fancy. And then you will solve for your t and then your o, okay? For your t, you need to find the t-test statistic. That is by taking the slope itself, whatever that might be, of your line. So remember, this is the lowercase b, right? So this is the predicted slope. The slope that is used in your regression line. Minus the null. Be aware that the null is always 0 in this case. Divided by the standard error of your slope. And that'll be presented in data output. They have to give that to you. Okay. So again, for the cheap seats, you will take the predicted slope in your line. So like when you do y hat equals Oh, goodness me, not x, equals a plus bx. This b here is the slope that you're going to use, minus 0 divided by the standard deviation of your slope. So the standard error there. And then remember, of course, that if it's a one-tailed, a two-tailed test, these are the two options. You either have a one-tailed upper, a one-tailed lower, or a two-tailed test. Just make sure that you work with those accordingly, right? And that if you have like a one-tailed statistic, you double it, and then, of course, so on and so forth. You're going to want to obviously turn it into using TCDF, that is, turn this value into a p-value and then double it if that's what you're doing. Okay, so once you've made the calculation and you've got this t, you move on to O, and that's when you'll use TCDF. And with that, you'll do, right, the t critical value either as the upper or the lower, depending on where it sits on your graph. So be sure to visualize that. It's the same as we've always been doing, right? If you have a positive t, it's quite likely that that's going to be your lower and your upper is going to be 100,000. If you have a negative t critical value, or test statistic, I should say, it's very likely that that will be your upper and your lower will be negative 100,000. And then whatever you get, double it if you want to make it a two-tailed test. And then for degrees of freedom with that TCDF, you'll notice it says on the slideshow, degrees of freedom this time are going to be n minus 2, not minus 1. And as we said in class, that's because we're working with two quantitative variables now. I had to check there to make sure I spelled it right. Variables. And because of that, we need to subtract 1 from each of them theoretically, right? But these are scatter plots. So each dot is representative of two coordinated variables that have been turned into one dot on a plot. So the scatter plot, for that purpose, we're going to do degrees of freedom n minus 2. Okay. You can see the way that the computer output shows it. When we use it, the B, you already learned how to do this when we look at the computer output. So really quickly, if you'll take a look at the slide, the value, the B right after the X variable that's been noted, is going to give you the slope. To the right of that is going to be your standard error for the slope. To the right of that, again, is going to be your T critical value. The last thing to note, though, is that the P value given to you to the right of that t-test statistic is going to be for a two-tailed test. So if they give you a bunch of computer outputs and they give you a p-value, remember to divide it by 2 if you're looking for a one-tailed test, because they gave you the two-tailed p. Anytime you have a computer output, it gives you the two-tailed. So be sure you know how to read those computer outputs that they'll put. I'll give you those. You'll get those on the AP exam. Be sure to come to me if you have questions about those. And the final part of phantoms that we have to go through here are the M and the S. And what are they? They're what you would imagine. They are simply about if the p-value is greater than or less than the alpha, whether we accept the null or reject the null, that's the same. The one thing that changes here is the phrasing. We either have convincing evidence that there is a positive or negative linear relationship between blank and blank, or we do not have convincing evidence that there is a positive/negative linear relationship between blank and blank. Now, if you're on that slide where it says significance test for slope, where M and S are highlighted, you'll see the way those are written out. And those are the ways that you should note this on an exam, a test, or in real life when you're doing this kind of applicative work. The final thing to note here as well is that if it's a does not equal situation, you could say that there is convincing evidence that there is a linear relationship between blank and blank. You don't have to say positive or negative, if and only if we're doing does not equal. All right, then you have a practice problem coming after, so hopefully that works well for you. The final thing I want to do with you here, and you can't believe it, I know you can't, I can smell that you can't believe it, but we're actually almost done here. I'm gonna switch all the way over to panic, right? And what I want to clarify here is for panic, so doing confidence intervals for these, we've already taken care of the P and the A. The P and the A will be the exact same as the P and the A for hypothesis testing, right? So liner for the assumptions, and the parameter will still be in regards to the true slope of the line that predicts Y from X. That's what we're calculating. The one change up here is the name for one. Instead of t-test, it is t-interval for the slope. then we have to calculate that interval. And how do we calculate that interval? Well, the equation that you'll see in your slides, but also present here, lowercase b for the slope of your assumed regression, right? This is the predicted slope, plus or minus. So this looks already like a confidence interval. Your t critical value, not the test statistic, the critical value times the standard error of the slope, so the standard deviation. So we see a repeat of the standard error and we see our slope again. But this t critical value, I need you to remember. The way we find the t critical value is the t critical value is do inf t, and then we do area to the left. So remember, if we were 95% confident, if that's our confidence level, find the midpoint between that and 100, and that'll tell you the area. 0.975 would be what we would use there. So area to the left, and then degrees of freedom, which, as we remember, same deal, n minus 2 this time. Okay. Now, hopefully this area to the left thing is a flashback to when we used to do this with other calculations. You need to find the midpoint between these two, right? Because we are looking for it in terms of the visualization. Whoop. We need to find the critical value up here. If the 5% of the 95%, for example, were split across two sides, so 2.5% and 2.5% on either end. And then, of course, the middle 95%. So we want to find the end with 97% of the data stretching all the way across and leaving 2.5% on the upper end, so to speak. Okay, that's theoretically where that t critical value will sit to grab everything we need. And that's how you'll find that. And then once you've done that, the final thing to note here is, of course, that t critical value is different than the t-test statistic that we have printed out on the computer. So do not use the t-test statistic for the t critical value. And for our conclusion, we will say, and you see this in the slides, this is the last thing we're going to do, we are blank % confident that the slope of the true regression line relating y in context to x, again in context, is between blank and blank. Legends, you now know how to take the computer output or the stated outputs, right? The given values from scatter plots and lines of regression, and how to turn those into a confidence interval using panic and these new steps. How to turn it into a hypothesis test where you test to see if there's actually a substantive correlation or not using phantoms. And effectively, you have done something that at the start of this year might have seemed impossible, which is you've made it through. You've done it. You have done every piece of content that we need to know for this year. Now it's all review, prep work, and an opportunity to shine and show off all that you know and really push yourself to the maximum. I'm so proud of you. I'm so thankful to be your teacher. Thank you for taking this journey with me. Thank you for doing it every day, a little bit at a time, step by step. It's an impossibility to tackle this all at once, but when we do it together and we break it down as a community, we get to go on this incredible journey. And along the way, I got to know you fully, and I'm so thankful. I'm thankful to get to do this beautiful material, and I'm thankful to watch you grow. So keep it up, never stop. Know that you are brilliant and that we are making a better world by understanding the data around us in an actual, applicable, substantive, nutritious way. Your legends, your heroes, study up, know your stuff, impress me with your debates and with your prep for the group test. You've got this, and the AP exam beyond us ain't nothing but a thing. This is Mr. Mays, adoring you, thankful to be your teacher, signing off.